This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 4 of a multi-part presentation. This part concerns Hilbert spaces. Hilbert spaces are not vector spaces that own an inner product. Vector spaces own a scalar product. Paul Dirac's Brocket combination turns vector spaces into Hilbert spaces. This part also investigates types of Hilbert spaces. Hilbert spaces are extended vector spaces. Vector spaces own a scalar product. Another name for scalar product is dot product. Spatial number systems own an inner product. Dirac's Brocket combination turns a vector space into a Hilbert space. This is a deeply rooted misconception of many physicists. Paul Dirac introduced a handy notation for the relationship that exists between the ingredients of a Hilbert space. The Brocket combination provides the opportunity to use real numbers, complex numbers, and quaternions as superposition coefficients. Dirac's Brocket combination turns a vector space into a Hilbert space. Dirac's Brocket combination selects a number system that is an associative division ring. Only 3 associative division rings exist: the real numbers, the complex numbers, the quaternions. The associative division rings exist in several versions. These versions distinguish in their symmetries. Dirac's Brocket combination selects a version with a unique symmetry. The generated Hilbert space inherits that unique symmetry. The Hilbert space archives the selected version of the selected associative division ring in the eigenspace of a reference operator. The Brocket combination defines operators, eigenvalues, and eigenspaces. In this way the bracket combination defines the capability of the Hilbert space to archive and retrieve the elements of the selected version of the associative division ring. First, we focus on separable Hilbert spaces. Inside separable Hilbert spaces, the applied sets of numbers are countable. With that restriction, the bracket combination turns the underlying vector space into a separable Hilbert space. By selecting a version of the number system, the symmetry of the number system is fixed. We treat the case that the Hilbert space applies quaternions to specify the values of bracket combinations. The format of the formulas that are shown also holds for complex numbers and real numbers. The values of bracket combinations will be used in linear combinations of vectors and as eigenvalues of operators. To make this possible, the bracket method distinguishes the vectors from the underlying vector space into two types of vectors with different arithmetic. The two types represent different views of the underlying simple vector space. The ket f is a covariant vector, and the bra g is a contravariant vector. The vectors f and g reside in the underlying vector space. The arithmetic of the ket vectors differs from the arithmetic of the bra vectors. The bracket combination ket f combined with g has a quaternionic value. If the underlying vectors f and g are equal, then the bracket combination can act as a metric. Since the product of quaternions is not commutative, care must be taken with the format of the formulas when quaternions are applied. The addition of ket vectors is commutative and associative. Together with quaternions, a set of ket vectors forms a ket vector space. Ket vectors are covariant vectors. A quaternion alpha can be used to construct a covariant linear combination with the ket vector f. The addition of bra vectors is commutative and associative. Together with quaternions, a set of bra vectors forms a bra vector space. Bra vectors are contravariant vectors. A quaternion alpha can be used to construct a contravariant linear combination with the bra vector f. For the bracket combination holds. For quaternionic numbers alpha and beta hold. This corresponds with another possibility would be and. This would have produced another notation for the bracket combination. Ket f combined with bra g is a simple constructed operator. For the orthonormal base, consisting of eigenvectors of the reference operator, holds. Eigenvectors belong to the underlying vector space. Eigenvalues belong to the natural parameter space, which represents a selected version of the applied number system. The bracket method enables the definition of new operators that are defined by quaternionic functions. The symbol f is used both for the operator f and the sampled quaternionic function f of qe. This enables the shorthand. For operator f, it is evident that for the reference operator R holds. This formula turns the separable Hilbert space H into a sampled function space. The hopping path that was introduced in part 1 is also represented by an operator. Its eigenvalues are the hop landing locations. These are the values of the point-like locations that correspond with the elements of the selected number system that point to the landing location. The hopping path operator embeds the hop landings into the selected version of the number system. This makes the hopping path operator an imaging operator. It maps the hopping path onto the selected version of the number system. The hopping path operator archives the hopping path. The eigenvalues of the hopping path operator are sequenced by a progression indicator. The sequence indicator can replace the real part of the eigenvalue and can replace the archived real part of the eigenvalue. This produces the sequenced hopping path operator. The chance that a hop landing arrives twice at the same location depends in the first phase of the selected set on the size and the recurrence rate of the hopping path. The chance that a hop landing arrives twice at the same location becomes neglectable on the second phase of the selected set. The same holds even stronger for the third phase of the selected set. This might be the reason for the existence of the Pauli principle. I is used to indicate the identity operator. For normal operator n holds. The normed eigenvectors of a normal operator form an orthonormal base of the Hilbert space. For unitary operator U holds. For Hermitian operator H holds. A normal operator n has a Hermitian part and an anti-Hermitian part. For anti-Hermitian operator A holds. This is a spatial operator, and differs from the mainstream interpretation. A Hermitian operator has real eigenvalues. An anti-Hermitian operator has spatial eigenvalues. The reference operator R is a normal operator. The reference operator has eigenvalues belonging to the selected version of the division ring. A non-separable Hilbert space uses a bracket combination that operates in the third phase of the selected associated division ring. Integration replaces summation. Continuity and balance equations become relevant. We will rephrase Dirac's bracket combination by using integration instead of summation. Every infinite-dimensional separable Hilbert space owns a unique non-separable companion Hilbert space that embeds its separable partner. The non-separable Hilbert space allows operators that maintain eigenspaces that in every dimension and every spatial direction contain closed sets of rational and irrational eigenvalues. These eigenspaces are uncountable and behave as dynamic sticky continuums. These continuums can vibrate, deform, and expand. Gelfand triple and rigged Hilbert space are other names for the general non-separable Hilbert spaces. In the non-separable Hilbert space, for operators with continuum eigenspaces, the bracket method turns from a summation into an integration. Here we omitted the enumerating subscripts that were used in the countable base of the separable Hilbert space. Instead, the integration applies the infinitesimal dv tau, that is taken from the continuum in the private parameter space. The shorthand for the operator f is now. For eigenvectors q, the function f of q defines as the function f of q is no longer sampled. The reference operator R that provides the continuum natural parameter space as its eigenspace follows from. The corresponding shorthand is. The reference operator is a special kind of defined operator. Via the quaternionic functions that specify defined operators, the claim becomes clear that every infinite-dimensional separable Hilbert space owns a unique non-separable companion Hilbert space that can be considered to embed its separable companion. The bracket method combines Hilbert space operator technology with quaternionic function theory and indirectly with quaternionic differential and integral technology. Like the situation in the separable Hilbert space, a grid overlay of the spatial part of the parameter space is applied to be able to integrate over the grid cells. The expected spatial value is averaged over a part of the real part of the parameter space. In the non-separable Hilbert space, the expected spatial value is defined as an average over the spatial part of the parameter space. The real part of the parameter space is usually held fixed, and the integration is done over the spatial part of the parameter space. The location density distribution is a continuous function with values corresponding to locations in the spatial part of the parameter space. Thus, the value q can be any value in the spatial part of the parameter space. A cosine function can be combined with a sine function that owns the same frequency into a complex number-valued exponential function. The imaginary factor e belongs to the direction of that same direction line. This sum has the remarkable property that p resembles the partial differential change operator for the direction e of p. We do not indicate in the exponentials the spatial direction number e with a vector cap. Instead, we use the convention that is applied in complex number versions of the exponential function. X and P are related via Fourier transform, and Fourier transform. In experiments, the spatial spectrum of a location distribution can be measured by a dynamic mask consisting of two sets of parallel bars that rotate in opposite directions. This produces a dynamic mask of coupled V-bars that constitutes a triangle wave when the masks passes a small slit. Next, an electronic OR application on a computer stops the high-order frequency contributions and a clean sine wave results. This equipment produces the modulation transfer function, MTF, of the slit. The MTF of a point is a mountain that has an ellipse at every horizontal cut. In the 70s, the author of this presentation used such equipment to measure the spatial frequency response of imaging devices that were lenses or image intensifiers. He used the old ELF transfer analyzer. The MTF of a point-like object is a mountain that has an ellipse at every horizontal cut. The peak at the top of the MTF is due to veiling glare. The Hilbert Book Model embraces the special set. This special set determines in detail how the Hilbert space behaves. For physical reality, one of the members of the system of Hilbert spaces plays the role of background Hilbert space. This special role confuses many scientists. This is also treated by Part 1, and will be subject of Part 5. The other members of the systems can be considered as representants of particles that move with their geometric center over the eigenspace of the reference operator of the background Hilbert space. This ends Part 4 of a multi-part presentation. This part concerns Hilbert spaces. Hilbert spaces are not vector spaces that own an inner product. Vector spaces own a scalar product. Paul Dirac's Brocket combination turns vector spaces into Hilbert spaces. This part also investigates types of Hilbert spaces. Part 5 concerns systems of Hilbert spaces and embedding and mapping of stochastic information. This occurs in the third phase of the special set.